Hello everyone, my name is Dounia Hammou. I am third year PhD student at the University of Cambridge under the supervision of Rafał Mantiuk, and today I'm going to present you our new quality metric, ColorVideoVDP-ML. So as you can guess from the name, it's an extension of ColorVideoVDP with a neural regressor from image and video quality prediction. So what is actually ColorVideoVDP? ColorVideoVDP is a perceptual quality metric based on psychophysical model of the human visual system to assess the visible distortion between two videos, which can be shown either as a distortion map, histogram, or the quality score. Because it's based on psychophysical model, it can natively account for SDR and HDR content, display specification, and viewing condition. Furthermore, it is a white box model based on low-level human vision, with very few learnable parameters allowing it to generalize well across diverse range of distortion. However, while it is based on low-level human vision, it does not really account for high-level vision. So let's take this as an example. So this is we're showing here the ColorVideoVDP heat map for one video. And ColorVideoVDP basically is given like the same importance or region of our frame. So basically it's assigning similar importance to the foreground and to the background. And in reality, most people actually just focusing on the foreground and ignoring or discarding the distortion that's happening in the background. Another problematic case of ColorVideoVDP is that it's penalized per pixel differences in like high entropy texture, for example, the curly hair of this woman. So as you can see, ColorVideoVDP is really penalizing the distortion here. In reality, most people discard the small texture differences. So here, in this work, we want to leverage the characteristic of ColorVideoVDP from the fact that it's well generalizable, it natively accounts for SDR and HDR content, and for the display and viewing condition. And we employ a neural regressor for higher level visual processing like saliency and texture similarity. So in this presentation, I'm going to delve into each block of our framework. And we're starting with the backbone, which is ColorVideoVDP. So as any other full reference quality metric, it's going to get as an input the test and reference video. One main block that really distinguishes ColorVideoVDP from other metrics is the display model. So ColorVideoVDP operates on physical units of the luminance. Hence, it uses the display model to actually estimate the exact light that's coming out of the display. So it's going to take into consideration the display luminance, the ambient light, as well if the display is SDR or HDR. And it does that by decomposing our inputs to the TKL color space. So we're going to get the luminance exactly in the exact light unit that is coming out from the display. So this is what allows it to natively account for SDR and HDR contents. We also get the red, green, yellow, violet channels. So this is kind of chromatic information which will allow the metric to find chromatic distortion. We're also going to apply temporal decomposition and get the transient channel. So this is information about the fast motion, which allow the metric to also account for any kind of temporal distortion. Then it will apply a multi-scale decomposition, exactly the Laplacian pyramid, which will allow us to get our input into multiple bands at different spatial frequency. And this step will allow us to encode our contrast and apply the contrast setting function, which will allow us to get our contrast for the test and reference in perception unit. So it just should be noted that all of this is happening for each of our channels. So here I'm just showing the luminance, but this is also happening for the red, green, yellow, violet, and also for the transient channel. ColorVideoVDP then applies contrast masking to get the perceptual difference. In reality, how ColorVideoVDP works is that it's going to put simply this perceptual difference and get the quality score. But here we're not taking only the perceptual difference, but we also take the test contrast, reference contrast as our features. And these features are going to provide us information on the high level visual processing. So because this kind of information that we're getting, so we're getting basically these bands at each different channel and each frame, so they are like gigantic kind of information that may take up to terabytes. So to reduce it, what we apply is that we're going to get, for example, our different features at, for example, here I'm taking the perceptual difference, so at different bands, and we're going to extract patches. So we want to take no overlapping patches, and they're going to be the same size across all patches, all bands, and each patch size is the number of pixels per visual degree. Then for each of this patch, we're going to calculate the mean and standard deviation. So this allows us to get for each patch at each different band and each different frame exactly 24 features. So this is for two statistics, which is the mean and standard deviation, and for different 4 channels, which is again the luminance, red, green, yellow, violet, and transient channels. So we're going to get 8 features per each one of them, so at 24 features in total. And this step will not only help us to reduce the size, but make our training of our neural regressor basically more efficient. So for the regression network, we want our network to learn high-level visual processing, for example, saliency and texture similarity. So in this work, we experimented with two different networks. We employ an MLP and transformer. So let's start with the first one, where we call saliency-based regression network, or directly ColorVideoVDP-ML saliency. So the idea behind this network is that we want to use two MLP predictors, one for distortion and one for saliency. So the distortion predictor is going to take the perceptual difference feature. So again, this feature is only per patch in each band at each frame. So it's going to take that and then predict one score that's going to represent amount of distortion that's appear in this patch. The saliency predictor, on the other hand, is only taking the feature from the test and reference contrast and predict some kind of salient information, or like a score that represents the salient information for this patch, and is going to get two-way the result from our distortion predictor. And then all the different scores are going to be averaged across each patch, band, and frame. It should be noted though that our saliency predictor is not explicitly trained on salient ground truth data. What we're doing is that we're training both our distortion predictor and our saliency predictor on quality datasets, and we want our saliency predictor to learn this kind of salient information implicitly. However, one big issue with this network is that it's taken a single patch feature as an input. So if you imagine that we have one salient patch, probably the patch next to it is probably going to be salient as well. But this kind of network cannot learn this relationship between the different patches. So that's why we also experimented with transformer. So here we are applying a very simple architecture. So we're going to have our different features for all patches inputted to our transformer encoder. So in these as well we're using, again, like any traditional transformer architecture, we first have a patch encoding. Here we're going to use a simple linear layer because our features are already have meaningful information in meaningful units. And then the encoded patches are going to be inputted with the CLS, which is a learnable token, to the transformer encoder. The results from that are going to be inputted to an MLP, and then the score that we're going to get, which is for each band at each frame, is going to average across all of them to get a quality score for the video. One thing that you can see here is that we don't really have positional embedding added to the encoded patch. We actually tried that, but it gave us slightly worse results, so we didn't really include it. Another thing is that we didn't really learn attention between different band and different frames just because of the complexity, and we had like smaller time for the challenge, so we couldn't really test that yet. But we also know that, for example, information across the different bands are similar, so we think it may not bring much information. So both of our network, ColorVideoVDP-ML saliency and transformer, has been trained on 4 different training datasets. So we have included the challenge dataset, UPIC, Live HDR, and XR-David datasets. So training on multiple datasets allow our network to generalize on SDR and HDR content, on images, videos, and multiple types of distortion, so like streaming distortion, image distortion, and display distortion. And this was only possible because all of our datasets are scaled in GOD units, which allow basically to have consistent quality across the different datasets. Not only that, but we are actually testing on 8 different datasets, and all of these datasets were used to monitor our training, select the checkpoint, and prevent overfitting of our model. So let's start by looking at our network performance. So here at the beginning, we're looking at the ColorVideoVDP-ML transformer and saliency against ColorVideoVDP on the challenge datasets. So again, because the datasets contain a lot of content with like an obvious salient object, you can see that ColorVideoVDP is performing very poorly on them. In comparison, ColorVideoVDP-ML transformer and saliency is showing like a drastic improvement compared to ColorVideoVDP, and is showing very high performance. Here we're showing the comparison between them again, but on all validation datasets. So as you can see again, both ColorVideoVDP-ML saliency and transformer are doing so much better than ColorVideoVDP on the challenge dataset, as well, for example, on UPIC datasets. However, on other datasets like Live HDR, XR-David, HDR VDC, Live Mobile, Live HDR, you can see, for example, that ColorVideoVDP-ML transformer is doing similarly. That's because ColorVideoVDP was already doing so well on these datasets. ColorVideoVDP-ML saliency actually is showing kind of overfitting. That may be the reason for the kind of simple architecture we use for that. And you can see it's overfitting on the Live Mobile dataset, which is the dataset that contains some kind of transmission distortion. So you can see that this metric just doesn't generalize as well as ColorVideoVDP-ML transformer. Now we're going to compare ColorVideoVDP-ML transformer with other metrics. So we actually looked into multiple metrics, but here I'm showing the 3 most interesting results. So here we are showing topic quality metric. So this is another metric that uses transformers inside the architecture of the metric, and you can kind of see that it's really perform well on the challenge datasets. However, ColorVideoVDP-ML transformer is still doing better than it, and you can see it's also doing better. It's not doing so well, for example, on LiveVQA and XRDavid. So in general, ColorVideoVDP-ML transformer is doing either similarly or so much better compared to topic. VMAF, on the other hand, is like a known quality metric that do so well on datasets that contain swimming distortion. And you can see that it's doing ColorVideoVDP-ML transformer is doing similarly to VMAF on more swimming distortion. However, on the challenge dataset, you can see VMAF is not doing so well, and that again is similar reason that VMAF is assigning similar importance to the foreground and background, which our metric is not doing anymore. Plus, VMAF only specializes on swimming distortion, so it cannot really generalize well on new distortion like XRDavid. And here we can really see the benefit from our model being trained on multiple datasets, because the fact we can train on multiple datasets, we can make our metric generalize to any amount of distortion as we can. LPIPS, on the other hand, is a quality metric that is pretty well known, but you can see it's not really doing well on most of the datasets, especially on the challenge datasets. So in summary, our metric ColorVideoVDP-ML transformer show like promising result, and we can see that surpass or do similarly to most like state-of-the-art metric on all quality datasets. To assess more the effectiveness of our metric in learning kind of saliency and similarity texture similarity information, here we would visualize the distortion heat maps. So here we start by ColorVideoVDP-ML without any test and reference contrast filters. So basically just imagine a distortion predictor, which is similar to what original ColorVideoVDP is doing. So you can see we still see this issue that it's giving similar importance to the background and the foreground. For ColorVideoVDP-ML saliency, we see less of this problem. However, we see it's still accounting for a lot of distortion in the background. On the other hand, ColorVideoVDP-ML transformer is not really giving any importance to the background. It's mostly focusing on the foreground, and it's also not really penalizing for like small difference in texture, which is similar to how like human observe distortions. So in conclusion, in this work we introduced ColorVideoVDP-ML. This work showed us that psychophysical model of the human vision can be combined with machine learning models. This allows us to improve ability to generalize, to account for ASR content, to account for display and viewing condition. Plus this ML here allow us to learn high-level vision phenomena like saliency and texture similarity. We can also see that training on a large data, so basically here we had 4 training datasets, will allow our metric to generalize better on multiple types of distortion. However, this was only possible because all of our datasets were scaled in the GOD units. So, thank you very much for your time. I hope you liked the talk. Do you have any questions?